A soft drink filling machine, when in perfect adjustment, fills the cans with 12 ounces of soft drink. Overfilling or underfilling is a serious problem. A random sample of 60 cans is selected and the contents measured. The sample yielded a mean content of 11.91 ounces. The population standard deviation is assumed to be 0.24 ounces. Test to see if the machine is performing okay using a 0.01 level of significance. What action, if any, should be taken? Okay, our population are the cans of soft drink. The population mean will be the mean number of ounces in the cans. We're testing to make sure that the machines are running well. And we will assume they are, that they are filling the cans to 12 ounces. The alternative would be that they're not. And based on our sample of size 60, we may have some evidence that they could be underfilling the cans a little bit. Now again, we'll run a test to see if this is strong enough evidence to say that there really is a problem and maybe we need to shut the machines down. Remember, this is just from a sample. This is just an estimate of the population mean. So 11.91 is not mu. It's a sample average. And it's evidence, maybe, that the machines are underfilling. But we know from the sampling distribution that if the machines were actually filling the cans to 12 ounces on average, 12 ounces would be the center of the sampling distribution. And the sample means would be distributed according to that distribution. So it's not surprising that even if the null were true, that the sample means would be a little off from that. Because again, they're coming from samples. They're estimating the population mean. Now we are testing, actually in this problem, we are testing on both ends. So what is called a two-tailed hypothesis test splits alpha. Our alpha is equal to 0.01, and if we split that, we'll have 0.005 on both sides. So in a two-tailed hypothesis test, we have two decision lines. And our rejection region is basically this bottom interval along with the top interval. Now, how do we find the z alpha over 2 values for those decision lines? This will be standard normal because we have a large sample, and in this case we actually have the population standard deviation. By the way, this wouldn't be uncommon in a situation like this because this value of 0.24 ounces was calculated probably from many samples, understanding the capability of the machines. They're collecting data on this same process over and over again. So they have a very reliable estimate of the population standard deviation. So much so that they're calling that sigma. So sigma over the square root of n would be 0.24 over the square root of 60. But getting back to finding the z values for my decision lines here, I need to go to the standard normal table. Now for the situation that we're in here, this upper tail end would be 0.005, and I need to get the z value for that. So I'm going to be working backwards in the table. So what I'm going to have to look up in the table is 0.5 subtract 0.005, 0.495. And I'm going to need to get as close to 0.495 as I can get so that I can associate that with a z value. It appears that it's right between 0.4949 and 0.4951. and that occurs in row 2.5 and in columns 0.07 and 0.08. So my z-value would be 2.57 or 2.58. I'm going to interpolate that a little bit. Right between the two would be 2.575. So 2.575. So going back to my distribution, I'm at a negative 2.575 and a positive 2.575. And I'm going to reject H sub 0 if my test statistic is less than or equal to negative 2.575, or my test statistic is greater than positive 2.575. So those are my rejection regions. And now we need to see what that test statistic is. What is the test statistic for the 11.91 ounce sample mean? How far away from the 12 ounces is that in standard deviation units? So I would need to divide by the 2.4 divided by the square root of 60. And I get negative 2.905. And that is enough evidence to reject H sub 0 since negative 2.905 is less than negative 2.575. So the 11.91 ounces is down here somewhere, because it is a little bit further to the left than my decision line. So it is far enough away from 12 to go ahead and reject H sub 0 and conclude that the machines need to be adjusted. Because when we reject the null hypothesis, we are saying that the alternative is true and that the average amount of soft drink going into these cans is not 12 ounces. Or, I should say, significantly different than 12 ounces, to the point where we would shut the machines down or try to make some sort of adjustment. Now again, as before, let's look at this problem and find a p-value. The p-value for a two-tailed test works a little different. The first thing I would need to do is find the probability of being less than the 11.91. In other words, the percent of sample averages to the left of the 11.91. Now that is at z location negative 2.905. So I'll be able to get that value by going to the standard normal table and looking up 2.905, which I would have to round to 2.91, and then by symmetry I could get that. So let's go to the standard normal table. So I have a z-value of negative 2.905. By the resolution in this table, I'm going to have to round that to a negative 2.91, and I'd be able to look that value up. Also, as you know, the standard normal table works on the right side for the positive, but by symmetry we'll be able to figure out what we need. The 2.91 would be down here in row 2.9 and then in column 0.01, so my value would be 0.4982. So what I'm getting there is 0.4982 on this end. That's associated with my z-value of 2.91. and then I would be able to get the area here by subtracting 0.4982 from 0.5, and that would be 0.0018. And by symmetry, that's the value I need. So this area down here is 0.0018. For a two-tailed test, the p-value is equal to 2 times 0.0018, which equals 0.0036. And then 0.0036 is less than 0.01. So reject h sub 0. And again, we expected the same conclusion. The p-value is just another way of looking at it. To make a little bit of an argument as why we would multiply this by 2 is, if you look at the lower end here, that area is 0.0018, and it's smaller than 0.005, and so it is telling us that the 11.91 is further out. It's past that decision line, and we can go ahead and reject. But my original alpha value is 0.01, and I would want my p-value to compare to that. So since I split that on both ends of the distribution, I'm going to double the 0.0018 so I can compare it to the original 0.01, and that's why you are doubling it.